This is the third video of Chapter 17 dealing with sound. This one is on the Doppler effect. A Doppler effect is experienced whenever there is relative motion between a source and an observer. If the relative motion is toward, then the observed frequency will be higher. And if the relative motion is backing away, then the observed frequency will be lower. So if the two are moving towards each other and somehow, either the source moving towards the observer or vice versa or both, if the distance between them is getting shorter, the observed frequency will be higher. And if the distance between them is getting larger, the observed frequency will be lower. This is our general intuitive approach to the Doppler effect. This is a phenomena common with all harmonic waves, including light. There's a Doppler effect associated with light. We know that most of the universe is expanding away from us because we observe a Doppler shift in that direction. Let's see how this might work. Let's say I have a source. In this case, we're going to be using a source of sound. I have a source of sound over here, and it is putting out wavefronts towards me and moving my eardrum back and forth so I can hear the sound. So if we neither one of us move, the actual wavefronts it's putting out with the actual frequency it's putting out will be hitting my eardrum and giving me exactly the same frequency as being put out by the source, and hence I will hear the frequency of the source. So the wavelength's unchanged. What happens if I start moving towards the source? So the source is putting out these wavefronts at a particular frequency, and I just heard a wavefront, and I start moving towards the source, so I'm going to pick up the next wavefront a little bit sooner, and I continue moving towards the source, and I'm going to pick up the next wavefront a little bit sooner as well. So as far as I'm perceiving things, even though the wavefronts haven't changed, I'm going to pick up them sooner. I'm going to hear a higher frequency of those wavefronts than if I had just been standing still. So if I am the observer moving toward a source, I'm going to pick up more wavefronts per time, and I will hear a higher frequency. The way this might work is that the observed velocity of sound that I would get as I'm moving towards the source is equal to the actual velocity of sound, 343 meters per second, plus the velocity of the observer, my velocity. So I'm going to add my velocity to the velocity of sound as far as this effect is concerned. So my observed frequency, f prime, is going to be my observed velocity of sound, v prime, divided by the true wavelength of the sound. That's going to be the velocity of sound plus my velocity divided by the wavelength of the sound. So we have that the observed frequency is going to equal the actual frequency of the source times 1 plus my velocity, the velocity of the observer, over the velocity of sound, this fraction. Now, my velocity for practical purposes might be 1 meter per second. If I'm just walking towards the source, I might be moving at 1 meter per second, while this velocity of sound, this v in the denominator here, is 343 meters per second. So this fraction, v naught over v, could be very, very small. And for most practical purposes, for everyday life, it's going to be so small compared to 1 that the observed frequency is going to be pretty much equal to the actual frequency of the source. So for most applications in everyday life, even though I'm walking around, I'm going to still hear the frequency of the source. It's not going to change much as far as I'm hearing it. However, if I'm moving towards the source at the velocity of, say, 60 miles per hour, which is on the order of 30-some meters per second, then this fraction of 30-some meters per second over 343 meters per second could be on the order of 1/10. And hence I would have 1 plus 1/10. I would increase my frequency, observed frequency, by, say, 10%. So, if the frequency we're putting out, say, middle C on the chromatic scale, I might hear a frequency that is 10% higher, which could be 2 notes higher on the chromatic scale. So instead of middle C, I'm going to hear maybe an F on the chromatic scale, and hence I'll hear a higher frequency. So instead of I'll hear like that, or even higher. So I'll hear a note that is a couple notes higher than what is actually being put out by the source. Similarly, if I have a source like this, and it's putting out wavefronts like this, and if I'm standing still, I just hear those wavefronts exactly what the frequency as they're being put out by the source. But if I start moving away from the source, then let's say I received a wavefront here, and then another one's just about to come in, but I start moving away, so it takes a little bit longer to get to my ear. And the one after that is coming here, and I've been moving away, and finally it takes a little bit longer to get to my ear as well. So if I start moving away from the source, I'm going to pick up these wavefronts in a little bit extra time. In other words, I'm going to have a less frequency per time than if I'd just been standing still, because the wavefronts have to take that much longer to get to me. Hence, my observed frequency will be lower than the actual frequency put out by the source, and I will observe something different than the source. So in this case, the speed of sound that I observe, v prime, is equal to the actual speed of sound, v, minus my velocity. And so that's going to be v minus the velocity of the observer. So the observed frequency will be this modified speed of sound divided by the actual wavelength of the sound. That will be the velocity of sound, 343 meters per second, minus my velocity divided by the wavelength of sound. And so I get this. The observed frequency will equal the actual frequency put out by the source times 1 minus my velocity divided by the velocity of sound. Again, if it's everyday life and I'm just walking around and I'm going 1 meter per second and the velocity of sound is 343 meters per second, this will be a fraction of 1 over 343, and that's going to be pretty insignificant compared to 1, and hence for most practical purposes I'm still going to hear the actual frequency put out by the source. So for everyday life, just walking around, even running around, I'm still going to hear the true frequency of the source. But if I were moving away, say at 60 miles per hour and 34 meters per second, then this fraction is going to be on the order of 1/10, and then 1 minus 1/10 will give me about 0.9. So in other words, I will reduce my observed frequency by 10% from the actual frequency put out by the source. And that could be significant. So on a chromatic scale again, that could be a couple notes on the chromatic scale. Alright, so I can change the observed frequency just by moving towards the source at a relatively great speed or moving away from the source at a relatively great speed. What about the source? Let's say the source were moving toward me. It's putting out a wavefront every so often, and I'm hearing that frequency it's putting out. But if it's moving towards me, then it's going to put out a wavefront with a little bit less distance from the previous wavefront. In other words, it put out a wavefront, and now it's moving towards me, and it's putting out another one, and the wavelength is effectively shortened from what it normally would be. So by the source moving towards me, I'm going to have a shortened wavefront. This shortened wavefront is going to equal the velocity of the source times time, and that's going to be equal to the velocity of source divided by the frequency. So I'm going to have an observed wavefront equal to the actual wavefront of the sound minus this correction for the velocity of the source. With a little bit of algebra, we can solve for the observed frequency under these conditions, and we have that the observed frequency is equal to the actual frequency of the source times the velocity of sound divided by the velocity of sound minus this correction for the velocity of the source. So this V sub s is the velocity of the source. So we have the velocity of sound 343 meters per second over 343 meters per second minus whatever the velocity of the source is doing. If it's only moving at 1 meter per second, then this fraction, 343 over 342, is going to be very close to 1. And the observed frequency will be very close to the actual frequency put out by the source. However, if this source is moving at 60 miles per hour, 30-some meters per second, then this will be a fraction of 343, say, over 313. It'll be a fraction of about 1.1, and it will increase the frequency by 10%. So if this source is moving at me at 60 miles per hour, I will hear a frequency that's increased by 10%, and if I'm at 440 hertz, concert A, then the frequency I would hear would be maybe a C above that, a couple of notes above that on the chromatic scale. So instead of I'll say something like that. So I will hear a higher frequency than what actually is being put out by the source. A similar argument would be if the source were moving away from me. It's putting out these wave fronts, but as it's moving away, it's effectively increasing the wavelength of the wave fronts that it's putting out towards me. The observed frequency under those conditions would be the velocity of sound over the velocity of sound plus the velocity of the source. And again, if the velocity of the source is minimal, then this won't change the observed frequency at all. But if the velocity of the source is significant, say on the order of 60 miles per hour or more, then I will hear an observed change in the frequency, maybe a couple of notes on the chromatic scale. So we wish to summarize all of this in one neat mathematical formula. It looks like this. The observed frequency, f prime, is equal to the actual frequency put out by the source. If you're right at the source, you would hear this actual frequency, times this, the velocity of sound, plus or minus the velocity of the observer, over the velocity of sound, minus or plus the velocity of the source. So there's several things that could change here. The velocity of the observer, either moving toward or backing away, or the velocity of the source, either moving toward or backing away. In this equation, the numerator is the velocity of the observer, the denominator is the velocity of the source, and the top signs in this equation refer to the motion of one toward the other. So if I'm in the numerator and I'm dealing with the observer, if the observer is moving toward the source, I'm going to use the top plus sign in the numerator. And if the source is moving toward the observer, I'm going to use the top minus sign in the denominator. The bottom signs in this formula deal with backing away. So if I am in the numerator and I'm the observer, if the observer is backing away from the source, then I'm going to use the bottom minus sign. And if I'm in the denominator here, and the source is backing away from the observer, then I'm going to use the bottom plus sign here. So top is toward, and bottom is backing away. And you have to put yourself in the shoes of the respective combatant here. If you're the observer, you have to put yourself in the shoes of the observer and then realize either the source is over there or over there. And if I'm moving away from it, I'm backing away. And if I'm moving toward the source, I'm moving toward. So you have to put yourself in the shoes of the observer in this case and think about where the source is and what you're doing, whether you're moving in that direction or away from that direction. Same thing with the source. Put yourself in the shoes of the source, and if the observer is somewhere over there, if I'm moving in that direction, I'm moving toward. And if I'm moving away from that direction, I'm backing away. So even though the relative motion of the two could actually be gained larger, we have to think of the individual combatants in this and put yourself in shoes individually and see what they're trying to do as far as using this equation properly. Let's try this out. An ambulance travels down a highway at a speed of 75 miles per hour, its siren emitting sound at a frequency of 400 hertz. What frequency is heard by a passenger in the car traveling at 55 miles per hour in the opposite direction as the car approaches the ambulance? So in this first case, we have the ambulance moving one direction, which is the source, moving at 75 miles per hour, which we multiply by 0.447 to get 33.5 meters per second. And we have the observer in the car moving toward the ambulance, moving at 55 miles per hour, which we multiply by 0.447 to get 24.6 meters per second. In this particular case, if I put myself in the shoes of the observer is moving, let's see, as you're looking at, the observer is moving toward the ambulance. The ambulance is somewhere here, and the observer is moving in that direction. So the observer is moving toward, I'm going to use the top plus sign in the numerator for the observer. The ambulance is somewhere over here, and it's moving toward the observer. Somewhere over here is the observer. The ambulance is moving in that direction. So the ambulance is also moving toward. I'm going to use the top minus sign for the source. So my observed frequency is the actual frequency put out, 400 hertz, times 343, the velocity of sound, top plus sign. The observer is 24.6 meters per second. And then I have 343, velocity of sound, top minus sign, because toward for the source, 33.5 meters per second for the source. Both of these effects are going to have the effect of increasing the frequency, and we're going to have a observed frequency of 475 hertz from an actual frequency of 400 hertz. So that could be 3 or 4 notes on the chromatic scale. What happens when they both pass each other? So in this case, the car is backing away from the ambulance because the car has already gone past. Ambulance is somewhere over here, and the car is going the other direction. And same thing with the ambulance. The ambulance is moving like this, and the car is somewhere over there, and the ambulance is moving in the opposite direction. So in this case, we have the actual frequency put out by the source. Now the observer is backing away, so we're going to use the bottom minus sign in the numerator. And the source is backing away, so we're going to use the bottom plus sign in the denominator. Both of these are going to have the effect of reducing the frequency. And we'll have an observed frequency of 339 hertz, which could be several notes on the chromatic scale below the actual frequency put out by the source. So we could have a higher frequency as the source is coming in and the two are approaching, and then as they pass, we pass through the actual frequency, and then on the other side we have a lower frequency. So it'd be like that. As the two are passing each other, we have a constant higher frequency pass through, and then a constant lower frequency of this as observed. Let's try this. Standing at a crosswalk, you hear a frequency of 560 hertz from the siren of an approaching police car. After the police car passes, the observed frequency of the car is now 480 hertz. Determine the car's speed from these observations. In this case, the observer is not moving, so the observer's velocity is just 0. So we have where the police car is approaching, the observer's velocity is 0. It doesn't matter that we have a plus or minus here. And the numerator will just have the velocity of sound. And as the source is approaching, moving toward, then we're going to use the top minus sign in the denominator. So our first observed frequency of 560 hertz will be the actual frequency of the source, which we don't know what that is, times the velocity of sound over the velocity of sound minus the velocity of the source. And then, as the source moves past and is backing away, again we have the velocity of sound in the numerator, but now we're going to have the velocity of sound plus the velocity of the source because we're backing away, so we're going to use the bottom plus sign in the denominator for the source, and we were told that that was 480 hertz. We still don't know what the actual frequency of the source is, and this corresponds to a B, but we're going to take the ratio of these two equations, and if we do that, we'll have 580 divided by 470. The frequencies of the actual frequency of the source will cancel out, and so will the velocity of sound in the numerator. And so I'm going to have 1.17, which is this fraction, times velocity minus velocity of the source will equal velocity plus velocity of the source, and we'll solve this for the velocity of the source, knowing that the velocity of sound is 343 meters per second. So we have the velocity of sound times 1.17 minus 1 is equal to the velocity of the source, 1.17 plus 1. And hence, the velocity of source will be equal to 0.17 over 2.17 times 343, 26.9 meters per second, which would be around 60 miles per hour. This is one way that the Doppler effect can be used to calculate how fast a source is moving. Or you can use the Doppler effect and bounce it off a source, and that change frequency as it bounces off will tell you the information you need to learn how fast that object is moving. And that's how a radar gun works. So in this case, we're moving at 60 miles per hour, and you can tell that that's how fast the car is moving. All right, one final example. Problem: a fire engine moving to the right at 40 meters per second sounds its horn, frequency 500 hertz, at two vehicles shown below. We have a red car that's stationary, and we have a blue car that's moving at 30 meters per second at that moment, passing the red car. And a fire engine moving at 40 meters per second. So in relative sense, the distance between the fire engine and the two cars is getting smaller in either case, so we should observe a higher frequency in either case. So what's observed by the blue car? Well, the observer is backing away from the source. Over here is the source. As you're looking at, over here is the source, and here's the blue car, and the blue car is moving away from where the source is. So even though the relative distance is getting shorter, it's the intent of the observer to back away. The observer doesn't know what the source is doing. The source is somewhere over there, and it's my intent to move in the opposite direction. So I am backing away from the source. The source sees the observer over here and is moving in that direction. So the source is moving toward the observer. So we have mitigating things going on here as far as the frequency is concerned. For our equation, we're okay. We have that the observer is backing away, so we're going to use the bottom minus sign, and the source is moving toward, so we're going to use the top minus sign in the denominator. So as far as mathematics goes, we have 500 hertz for the actual frequency of the source, velocity of sound 343 minus the velocity of the observer 30 over 343 minus the velocity of the source, and this gives us an actual frequency observed of 517 hertz. So even though we have these mitigating things going on, all things considered, we are getting closer together, and the frequency did go up a little bit to 517 hertz. What about this red stationary car? Now the velocity of the observer in this case is 0. The source is still moving toward the observer, towards the stationary car, so that will still be a minus sign for the top minus sign in the denominator. So the observed frequency for the red car will be the velocity of sound 343 plus or minus 0 over 343 minus 40 for the velocity of the source. So this is going to give us an observed frequency for the red car of 566 hertz. So the blue car and the red car, I say car and van, should be blue car and the red car, are two observers who are at the same place in the universe at the same moment in time, because the blue car is passing the red car at the same moment in time at the same place in the universe, yet at this moment they hear different frequencies. Wow. You can be at the same place in the universe at the same moment in time and observe something different from someone else, and it's perfectly okay. The Doppler shift says it's perfectly okay to observe different things even though you're at the same place in the universe at the same moment in time. Wow, it chokes me up. Wow. How cool is that? Physics says it's okay to observe different things. How can you use this to your advantage? Let's say you were the defense main witness for the defense, and your client was accused of stealing $2 million. And you say, you know what? I know you've got your observer who says that my client put their hands on the $2 million and stole it. But you know what? Two observers can be in the same place at the same time and observe different things. And I've got an observer who says my client didn't take the money. And physics says it's perfectly okay to have two observers who say totally opposite, that they observe different things. So you have, since there's some level of doubt here, you have to let my client go free. Physics says it's okay. Just make sure that if your client did steal $2 million, that they can pay your $1 million fee for compromising your morals and defending somebody who is guilty. So that concludes our discussion of sound in Chapter 17, the third video in this chapter, and we're ready to go on into Chapter 18, dealing with standing waves and resonance.